Hey everybody, back for one more crash course review. This time dealing with the last topic that we need to go back and look at, which is rotation. If you remember, we kind of separated this into two different units or two different chapters. The first one was a combination of chapter 5 and 8. It was kind of the intro, the lighter, the easier part. And then there was chapter 8, which was kind of the juggernaut, the big one that dealt with all the rotational stuff. So this video will review some of the main concepts in both of those chapters. The first one here were basically the equations that we looked at, which were kind of a hodgepodge of different topics, but it started with centripetal acceleration. Then we did Newton's universal law of gravitation. We did some other gravitational stuff there, including this one, which is field strength, gravitational field strength. And then we ended with torque as a way to get us thinking about the right topics for the next chapter. So this was the breakdown to look at centripetal acceleration first and some of the things that went in there. If you look at something that's traveling in a circle, one of the things in this chapter we said was that anything traveling in a circle, we could say we knew that it was accelerating because it was changing direction. So a change in direction meant that velocity was changing. And if you change velocity, then obviously that's an acceleration. So that's centripetal acceleration, these things moving in a circle. If you had something down here that was moving in this circle, we basically said there was two components to that. You had inertia that was trying to keep that thing moving in a straight line, but then you had this force that was being exerted towards the center of the circle, and that is what we call centripetal force. So the force that's causing this acceleration. So this is the diagram, and if you remember, we brought up centrifugal force or acceleration, which is that false force that works in the outward direction that we said actually isn't there. It's not a real force at all. So these are the two components. You would never want one of these diagrams to have an arrow that points away from the center of the circle. The acceleration is always towards the center of the circle, and that can be calculated just using this equation. So that was that in a nutshell. Newton's universal law of gravitation, remember, allows us to figure out how much force there is between two objects. And all we need to know are the two masses and their distance. Remember that g is a universal constant. You can find that on your data table to plug in there. It's a really small number, so you have to have some big numbers up here if you want to actually have a lot of force come out of this equation. So remember that. Remember that radius is squared down here, and that does have some implications in terms of the amount of force between two objects. So be careful with that. We also did this one. This one allows you to solve for the field strength around an object, gravitational field strength around an object, just knowing its mass and its radius. So you can plug into this and solve it out. Remember the units. G, of course, on Earth is 9.8, so we know the value of it, and we always called that usually meters per second squared. But remember, the equivalent unit to that is newtons per kilogram, how much force is acting per kilogram that the object contains. So this was another equation that we used. And then torque, pretty easy topic, was just the amount of force that was applied and how far away it was applied from the axis of rotation. So that was chapter 5, 8. Moving on to chapter 8, down here, some more detail stuff. If you remember, this chapter really has a ton of equations. I made you guys that special equation sheet. Hopefully you still have that around. I would probably recommend having that out for AP exam since you're allowed to have notes out. But that runs through basically all of them. Just to give you a quick review of what the chapter looked like, and the general idea is that we took all of our earlier equations, so like these are both chapter 2 equations, and we adapted them for rotation. And so basically what we saw was kind of a substitution of variables here. It was no longer like a linear velocity, which is v. It was now an angular velocity, which was omega. And then the d was no longer a linear distance. We substituted in, and we kept time the same. So there was t. So that was our new equation. Down here basically did the same thing. So no longer linear acceleration. Now it's angular, where we used alpha. And then we can substitute these guys also. Just like that. So we had a bunch of other equations also, so look over that equation sheet in your notes and the the PowerPoint and all of that stuff. But that was the general idea, is that we took all of our old equations basically from the whole year in this chapter and adapted them to things that were rotating, and that meant that new variables got introduced. So that gives you at least a little bit of the idea. Over here, just to kind of draw this out and kind of distinguish, we looked at a lot of these kind of diagrams. If we look at like a linear displacement versus an angular displacement, remember an angular displacement is literally the angle that gets moved through. Could be measured in degrees. Most of the times we measure these in radians. So if you remember that, like the units here were radians per second, and here radians per second squared, which we just called rads per second squared. But anyway, this was basically kind of what you were solving if you're solving that distance. And we would say that if you had an object here that moved across this angle versus an object out here that moved across that angle, both of those objects, so this guy and this guy, both have the same angular displacement. But if you look at linear displacement, this one's much shorter because it just goes here versus this guy out here that goes all the way along here. So same angular displacements, different linear displacements. Keep that in mind. All right, let's see. So moving on, rotational inertia. Basically, I wrote out a couple quick definitions here. If something has a high rotational inertia, it was slow to start. So if it's rolling down an incline, it does not speed up very quickly. If it has low rotational inertia, then it does. It speeds up really quickly. And remember, it all depended on where the mass was located. If you got the mass located close to the axis of rotation, then you got a scenario where you got a fast start. But if you took that mass and you spread it out and it was far from the center of rotation, then you got things where you would look at like high rotational inertias and slow starts. And if you remember, we had three equations that kind of helped us deal with that. We had hoops and rings, which the mass is very far from the center, which meant high rotational inertia, which is abbreviated with I, if you guys remember that. Disk puts some of that mass closer to the center, so you've got a 1/2 in there, and then the sphere basically kind of has the same idea as the disk, only now it's in three-dimensional effect, really, so that mass is more closely packed in around that center of rotation. So these were the three. We kind of made the comment, we proved it mathematically later on, that if you had these three all lined up, the one that reaches the bottom first is sphere, and then disk, and then hoop ring. And that's just based on slow start versus fast start on the incline. I think that's it for rotational inertia. Some other things that we hit. This was a long chapter. Other things that we hit, Newton's second law, which we adapted. So we did the same thing that we did with all the other equations. So instead of force, we were dealing with torque. So it's not just a force, it's where the force is applied at. So that's what torque was. And it's not just mass, it's where the mass is located also. So that was our I value, so rotational inertia. And then it's no longer a linear acceleration. We are now talking about alpha because it's a rotational acceleration, sorry. So that was our equation. We could plug in here and find out things like a disk that was accelerating or that sort of thing. So that was Newton's second law applied. Momentum and conservation. If you remember, angular momentum is abbreviated with an L. So this was the start anyway. Be careful with those I values because that'll change based on what the object is. So you might be looking at like a ring where you'd have mr squared here. You might be looking at a sphere where you'd have 2/5 mr squared to plug in. And so that changed things a little bit. I put conservation on there too. If you remember, a lot of times we had this kind of setup where something got changed during the course of the problem. Remember, this was like figure skater example. We got out those rotating platforms, and remember, if you had your arms held out, then you increased your I, and if I goes up, then omega goes down and you slow down. But then if you tucked in your arms, so in other words, you took your I value and you lowered it, then you saw this guy increase. And so you would speed up on that rotating platform. So you can kind of play the game and go back and forth with that. All right, and the last topic, which I think's the most major because it ties in a whole bunch of stuff, but energy and conservation. Remember, if you have something on a slope or an incline and it's rolling down the hill, then there's two types of kinetic energy. So here's like the general chapter 6 kind of setup, PE equals KE, but now we have to add KE rotational because the object is now rotating as it goes down the hill. And so this was kind of the general look for these problems. And then we could kind of go from there and write these out. I'm going to work these out a little bit for you. I've got you practicing some of these in the review for the week. 1/2 b squared. So there's that whole thing broken down. And then remember we did some work on this equation to kind of get it to agree with the other terms that are in here. And so one of the big things that we had to do was we had to use one of those earlier equations. If you remember this one, it's in the PowerPoint. It's on your equation sheet. But we used this and we rearranged it for omega. So we just did that. And then we substituted this in here. And what that did, I'm going to rewrite this so you guys can see it. This will help for sure on some of those review problems. I'm going to break this down. Let's say we had a ring. That way I can actually enter some r squared here for I. If it were something else, you'd have to put, if it were a disk, then you'd have to put 1/2 Mr. squared here. So it would look weird, but you'd have the 1/2 mr squared, that sort of thing. But now, since this is getting squared, and we've got V over R, I'm just going to go ahead and square those all in one step. On your example problems that you'll see in your notes and on the worksheets, we did that in a couple steps just to explain everything. But if you get to this point, then you can actually start to cancel stuff out because now you've got mass in each of these terms. So your masses will cancel, slash those guys out. You see that you got r squared, those cancel. And so now you can kind of reduce this down and you can combine like terms. So I'll go ahead and do that stuff while we're at it here. And we got these crazy equations that start with so much detail and they're so long, but then they boil down to very little once you actually run them through and cancel stuff out. The last thing to cover dealt with this same kind of setup, but we did something where we just kind of called it roll versus slide. So if you have this sort of setup and you've got one object that rolls and one that slides, the one that slides is always going to have the higher velocity down here or reach the bottom first because it doesn't have KE rotational. So basically all of the potential energy gets converted just into this versus if you have rotation, then this potential energy that you have stored gets split between some of these, and that affects the overall velocity and the amount of time that it takes to get down here to the bottom. So I'll just put something simple here. Slide wins. I think that's it. Guys, let me know if you have any questions. Good luck reviewing.